So, wait, I'll minimize this. Okay. So, today's lecture is analysis of variance and correlation. So, wait, how I pass this? Okay. My name is Walter Maru. I'm senior teaching assistant for the PPCR course. I'm also a plastic surgeon from Rio de Janeiro. I'm Peruvian, I live in Peru, but I did my plastic surgeon residency in Brazil. I'm a general surgeon and an MD. Now, this is what we should see today. As you see, it's a lot of stuff, but we'll go like in baby steps, so you will understand everything. Please, if you don't understand something, you can type your questions in the chat, or you can ask them directly through your microphone. So I'll see. Let's start with ANOVA, then we'll finish with correlation. With ANOVA, we'll start seeing the conceptual basis of comparing means. We'll understand a little bit about the statistical ratio when comparing means. Concept of variance is very important. Concept of ANOVA, one-way ANOVA, a little bit of math, sum of squares, mean squares, degrees of freedom, F statistic, F ratio, critical values, then multiple comparison tests, two-way ANOVA, repeated measures ANOVA, non-parametric ANOVA, which is Kruskal Wallis and Friedman, and we also have some STATA examples, which you'll do with me. You've got the data sets are on the website, so you can follow me in this data. Then we'll go a little bit to correlation, see a little bit about scatter plots, about the correlation coefficient, about the Pearson product moment correlation coefficient, the R statistic, Spearman rank correlation coefficient, the RS statistic, and we'll finish with some examples. We'll hope we'll have time to do everything. And let's start. Let's start with analysis of variance. Okay, the famous ANOVA. Wait. Okay. Here. Okay. We'll start by understanding a little bit about the conceptual basis for comparing means. You know, t-tests and analysis of variance, they rely on means. They compare means. Okay. So the concept of statistical significance for comparing means is based on the relationship between two sample characteristics. And if you understand this, you understand the basic of t-test and of ANOVA. It's like really, this is like the foundation of everything. These two sample characteristics are the mean divided by the variance. Okay? What I mean by mean? What I mean is like it's the difference in means. So in a t-test, you have two means. In an ANOVA, you have three or more means. Okay, so it's the difference between these means or between these groups that will give me the effect size. Okay, and the variance will be the variability of scores within each group. Okay, and why is this? Because why groups have variability? Because not all participants respond the same. So this variability within the group will be my error variance. So we're just now put a lot of attention here because we'll be talking a lot about between groups variability, which means difference in means, and within group variability, which means that participants do not respond the same within a group, so you will have this error variance. Okay, so it's means or difference in means divided by variance. That's like the basic of ANOVA. For example, here you have, this is a diagram of a perfect experiment, an experiment in which you repeat the experiment 100 times and you'll get the same result. For example, for the control group, you'll get 50, and for experimental group, you'll get 75. So every time you repeat the experiment, you'll get 50 units for the control group and 75 units for the experimental group. Sadly, clinical research is based not on perfect experiments, but on trials or experiments with people. And as I told you before, people does not respond the same every time, or they do not respond the same as one another, because we have special characteristics, or we have like different characteristics, and we respond different. So clinical research does not have this graphs of control and experiment, but graphs are more like B and C. Here you see what I told you. This is the mean for the control group, and this is the mean for the experimental group, you know? So this difference between the means, okay, will be my effect size. But within the group, you'll see that scores are distributed along this mean. And this is because we respond different to one another, okay? So for example, here I say that any given score is a composite of the effect size plus an error variance. For example, if I'm on this point, if I'm on this point because I am part of the experimental group, but I responded a little less than the mean. Okay, so I'm here. Another example, if I'm in this part of the graph, I'm part of the control group, but I have responded a little bit better than the mean. Okay, so this is why the score has part of the effect size and part of the error variance here. So that's easy to understand, I think. Okay, this graph C here, I've put it because just for you to see the difference between B and C. Here you can see that it's much easier to see the difference between groups in graph B than in graph C. Okay, and why is this? Because even though the means have the same separation, so that you have the same effect size, the variance is different. You have a smaller variance in graph B compared to a larger variance in graph C. So you'll see here that the bigger the variance, okay, the more difficult is to find statistical significance. Also, if the effect size is close together, if the means are close together, it's also difficult to find statistical significance. Okay? On the other side, if the means are more separated, you have a bigger effect size, and it will be easier to have statistical significance. And if the variance is small, it will be easier also to find statistical significance. So if you understand this, you understand like 90% of the lecture. Okay? Let's see. This is a little animation of how the statistical ratio works when comparing means. Okay? So here you see two groups, two means. The means are separated, so you have a bigger effect size. Okay? So this means it's easier to see the difference between the means visually. And this is another example. There you have your two means. Now, the effect size will stay the same, but your variance will reduce. So now it's easier to find statistically significant differences between groups. So remember, it's very important that you understand and you grasp this concept. The statistical ratio is very important, and if you have bigger effect size or bigger difference between means, you'll find it's easier for you to find statistically significant results. And if your variance is smaller, it also helps to find statistically significant results. Okay, let's go. So this is the statistical ratio. It's the difference between means divided by the variability within groups. Okay, put it from another way, it's the same as saying the difference between means is the treatment effect plus the error over the variability within groups, which is the error. Meaning that if I got a bigger treatment effect, okay, my numerator of the equation will be bigger than the denominator. And the bigger my treatment effect, my bigger the numerator. So the ratio will be bigger, okay? And as I say here, as the statistical ratio increases, the possibility of finding statistical significance is much higher. But not only this works if the treatment effect is bigger, this also works if the treatment effect stays the same and the error or my variability or my variance gets smaller, okay? If the denominator of this division gets smaller, my ratio will be bigger. Okay, I think it's easy to understand, but this is the basis of t-test and the basis of ANOVA. I'll continue. So now we finish looking at statistical ratios, and this is the other important concept we need to understand: variance. Okay. Here I have a question from Anosh Ahmed. Can I explain error again? Of course. Let me go back. Error is the variability within groups. Error is the variability. We as we are participants, as we are people, we don't respond the same as everybody else. So there's errors. So there's variability within the group. This variability will be the error variance. Okay. So, and my numerator in the statistical ratio will be the means. So if the means are separated, it's easier to find statistical significance. If my error of my my variance is smaller, it's much easier to find statistical significance. Okay, I'll go forward then. You see, easier to find significance, easier to find significance. It's very important you understand this. Okay, that was the statistical ratio. Now I'll talk about variance. Variance is very important. Variance is part of descriptive statistics, but you need to understand this pretty well because this is the basis of an ANOVA, which is analysis of variance. So variance is a measure of variability. Okay. So how can I measure variability of the variability or the dispersion of my scores around the mean? The easiest way to do that is by having some deviation scores. What is deviation scores? Every score is not in the mean exactly. Have you seen this bell-shaped curve? The scores are beyond the mean, or they are like at the back of the mean. They're not in the mean. Okay. So what you do is you subtract the score from the mean. Okay. That is what a deviation score is: the subtraction of the score from the mean. So the bigger your deviation score, the bigger the variability around the mean. Wait a second. I'll minimize this. Okay. So the bigger my deviation score, the bigger the variability around the mean. So then you can get a mean deviation score. No, because if you for example, if you try to subtract all my scores from my mean, I can have a mean of those deviation scores. It will be a very nice way to see my dispersion. Okay, but what's the problem? Is this a good idea? No. Why this isn't a good idea? Because if I subtract all my score from my mean, I will get 0. Why? Because the mean is a measure of central tendency. So here I put it. Means are central tendency measures. So it's a central balance point for distributions, meaning that scores will be equally dispersed above and below the central point. So if I subtract all my measurements from the mean, I'll subtract the same amount of measurements above the mean that the same amount of measurements below the mean. So in the end, I'll get 0. Okay. So what can we do to pass this problem? Because we can have any variability if it's 0. Well, how we go around this problem? Easy. Statisticians are intelligent people, you know, much more intelligent than me. So they squared the deviation scores to get rid of the minus sign. Okay, so this part of the equation of this part of the formula of variance is the dispersion score, but squared. And what is this called? This is called the sum of squares. Only this part of the formula of variance is called sum of squares. And why I squared my deviation score? I squared to get rid of the minus sign. So when I when I subtract all my scores and I square them, I won't get negative values. So then I won't get 0. Okay? And with this sum of squares, I will have a good measurement of variability and this or dispersion. But what's the problem with only having the sum of squares? We have one problem, that the bigger the sample size, the bigger the sum of squares will be. Because we will just be adding numbers, not really meaning that the variability will increase. We'll just add numbers. Because, for example, if I had like a sample size of 300 patients, I'll add like 300x minus the mean. So my sum of squares will be bigger than if I had a sample size of 10 patients. Okay? So what do statisticians thought about this? How did they go around this problem again? Well, they decided that to fix this problem, they could divide the sum of squares by the sample size, making the mean of variability or dispersion. So your sum of squares, which is this one, they divide it by the sample size. So then they don't have this problem, okay? And by doing this, you have sum of squares divided by your sample size, but as you are doing a sample size, you'll not divide by n, you'll divide by the degrees of freedom, okay? Which is n minus 1. And this formula, the sum of squares divided by n minus 1, is called mean square, which is the same as the variance. It's the same formula as the variance, okay? And here they ask me, why not divided by n? Because we are having samples. We are not using the whole population. If we'll use the whole population, we'll use n. But if we are working with samples here, we need to adjust our calculation using degrees of freedom. Because when we use samples, we normally underestimate the actual population result. So this is why we put -1 or -2 in some statistical test, just to do this small adjustment, because we are using samples and we are not using population. Okay, so I hope you all understood how the variance works and how the formula for variance works. Okay, so here you can see the concept of variance. Okay, this is the formula of variance, which is sum of squares divided by n minus 1. Okay, this is the variance. You can see here a really good example. What happened if you just subtract the score for the mean from the score and you add all of this, you will get 0. So this doesn't work to see our variability. So that's why we do the sum of squares, and we do this square. So the sum of squares, sorry, this is my deviation score, okay, which gives me 0. When we squared my deviation score, I've got my sum of squares, which is 273, okay? And this divided by my sample size n minus 1, I'll get a variance of 39.07. Okay, so we can go forward. Now, let's start talking about the concept of ANOVA, or analysis of variance. It can be used when, in many cases, when the independent variable has more than 2 levels, we'll use a one-way ANOVA. For example, an independent variable with 3 groups, or with 4 groups, or with 5 groups. When there are more than 2 independent variables, we'll use a two-way ANOVA. When their repeated factors are used to evaluate the performance of each subject, we'll use repeated measures ANOVA. When the independent variable has more than 2 levels and data is non-parametric, we'll use Kruskal Wallis ANOVA, which is an ANOVA using ranks. And when we have repeated factors are used to evaluate the performance of each subject and data is non-parametric, then we'll use the Friedman ANOVA. We'll see every one of these in a while. So in ANOVA, we will mix 2 concepts that we have just seen, statistical ratio and variance. Okay? That's why I explain both concepts right now. So in ANOVA, what's my statistical hypothesis? What's my null hypothesis? My null hypothesis in ANOVA is that all groups are equal. Group 1, group 2, group 3, group K. And my alternate hypothesis is that at least 2 means will differ. It's very easy there. So this is a very important slide. What's the concept of ANOVA? If I have 4 groups like here in the diagram below, okay, what I do first is I pull my 4 groups and create one big group, which is this big group. Okay, this big group is only the addition, the pooling of these 4 groups. Okay, and this big group will have a mean, which will be called the grand mean. This is the grand mean. Okay, and what is ANOVA? ANOVA is nothing more. Oh, sorry. ANOVA is nothing more than comparing the difference of the grand mean with the group means here. So it's like having the variance of the group means to the grand mean. That's ANOVA. So if you understand it, you can just go have breakfast and do another thing. Because this is all you need to know. Okay, you pull all the groups into one big group, then you have a big grand mean, and ANOVA is the statistical test which compare the difference of the group means with this grand mean. That's all. ANOVA, as it is a parametric test, has some assumptions. Samples must have a normal distribution. Samples must have homogeneity of variance. They must be independent samples, and they must be randomized groups. Okay. Okay. So we'll start with the sum of squares. We'll start with a little bit of math in ANOVA, which is really, really easy. What is the sum of squares? Remember in variance, I told you that the deviation square is called sum of squares. Here is the formula. Okay, here is the formula. Okay, so this is the same. This formula is exactly the same, but this is for ANOVA. This is for the total sum of squares. This is when we pull the 4 groups into one big group and we have the grand mean. Okay, then we'll have this. We will subtract all the scores from the 4 groups which are pulled according to the grand mean, and then we'll square it, and that's the total sum of squares. Here it is. Here is the addition of x minus the addition of x squared minus the mean squared, x squared minus mean squared. Okay, this is the mean. This is the formula for a normal mean. Addition of all my scores divided by my sample size. Okay, so this is mean and this is x. I've only squared it. Really easy. But that will explain my total variance. Okay, now that total variance, I will partition it. So I will partition my sum of squares. between groups variance and a within groups variance. The between group variance, as I told you in the statistical ratio before, the between group variance will show me the difference between means. So will show me the effect size, okay? And the within group variance will show me the between subject error or the error variance. It will show me the between subjects variability or the error variance, okay? So between groups will show me effect size, within groups will show me error. And here you can see that the total sum of squares, which we see here in the last slide, the total sum of squares equals the between groups sum of squares, which is my effect size, plus my within group sum of squares. Okay? Really easy. So I'll explain a little bit what's the between group sum of squares, which is the treatment effect. You remember what I told you about ANOVA? ANOVA is nothing more than comparing the grand mean with the group means. In this case, we have 4 group means, okay? And this is all that this formula says to me. Here, this is the grand mean, okay? This is the grand mean. And these are my group means. You see? This is, for example, the group mean, the group 4 mean. Group 4 mean is all the scores divided by my sample size squared, because it's sum of squares. Okay? Then I'll add my third group mean, which is all the scores in the third group divided by my sample size of the third group. And that's all. And as you see here, what this sum of square is doing is making a variance, is testing the variance between the grand mean and the group means. So it's like a variance within the variance. It's really nice. It's really clever. So as I put here, now group means are treated like scores from the grand mean. And that's how you get the treatment effect from an analysis of variance. That's why it's called analysis of variance, because you are analyzing variance of the grand mean and of the group means. Okay? This is all. And this is the very easy math you need to know, which is only squaring the group means and subtracting from the grand mean. Okay? Next. Now, I'll tell you about the sum of squares of the within group sum of squares, which is my error variance. This is not my treatment effect anymore, but my error variance. And what's this? It's nothing more than finding the variance of each group. Okay? So I put it here. Here we are finding the sum of squares of each group, of each group mean, and adding them up. That's all. Here is X. This means like my score, all my scores, and I subtract them from my group means. This is the group mean. For example, group mean 4 is all my scores in group 4 divided by n. So this is my group mean. Okay? This is my group mean, which I'll add my group mean 4, my group mean of group number 3, my group mean of number 2, and my group mean of group number 1, and I'll just subtract all the scores. It's very easy. And that's my error variance. So until now, we have been messing around with the top part of the variance equation, which is this. We have talked about total sum of squares, between group sum of squares, and within group sum of squares. But what was the problem with that? Remember, I told you before that the bigger the sample size, the bigger the sum of squares will be, because we will just be adding numbers, not really meaning that the variability increases. So you remember what I told you about statisticians, what they did? Okay, they simply divided the sum of squares by the sample size or the degrees of freedom. So that's exactly what we will be doing here. We will be dividing our sum of squares, our total sum of squares, our between group sum of squares, and our within group sum of squares divided by our degrees of freedom. That's very easy. They put me here, I didn't understand within groups. Within groups is only the variability within each group. That's all. So when I divide my sum of squares by my degrees of freedom, I'll get my mean squares, okay, or my variance. This is my variance equation, which is also called mean squares, okay? So statisticians here, I put, so statisticians decided that to fix this problem, they could divide the sum of squares by the sample size, making a mean of variability of dispersion. So this is called the mean square or variance. You remember I talked about it like 10 slides ago. So we'll do this with our between group sum of square and with our within group sum of squares. Between groups, and we will get our between groups mean square, which is nothing more than the between groups sum of squares divided by the degrees of freedom of our between groups. And to get the within groups mean square, we divide the within group sum of square divided by our degrees of freedom of the within groups. How do I get these degrees of freedom? Very easy. ANOVA have 3 types of degrees of freedom: total degrees of freedom, between groups degrees of freedom, and within groups degrees of freedom. These are the formulas, are really easy. For my total degrees of freedom is my total sample size, because this is used remember when we pull the 4 groups and we have this big group and this grand mean, okay, here the degrees of freedom from the total will be the whole sample size minus 1. The between groups degrees of freedom will be my number of groups minus 1. Okay? Why? Because you remember that in the between groups, we were doing an analysis of variance between the grand mean and the group means. Okay? So my sample there will be only my group means. If I have 4 groups, okay, my sample size will be 4. So this is why it's k minus 1. Okay, number of groups minus 1. And the within groups degrees of freedom is n, the total sample size, minus k. So now we'll talk about the F statistic. Okay, the F statistic is nothing more than a statistical ratio. And why it's called the F statistic? Because it was invented by Ronald Fisher. So his last name was Fisher, so he put his name to the statistic, F statistic. So it's nothing more than the statistical ratio we've been talking all the lecture applied to the variance, which the statistical ratio is difference between means divided by variability within groups. In this case, what's my difference between means in ANOVA? I took my between groups. In this case, my mean square of between groups. Okay, and what's my variability within groups, or my error? The mean square of my within groups. Okay, between groups, within groups. So that's my F ratio. Okay, if you understand the F ratio, you understand the ANOVA, because this F ratio is what you will compare with the chart of the F ratio distribution. And if this F ratio is bigger, is equal or bigger to my critical value, then my ANOVA will be, my result will be statistically significant. This is the F ratio. Okay, this is the same, the F ratio. Here, I say, when the null hypothesis is true and no treatment effect exists, the total variance in the sample is due to error, and the mean square of the within group is equal or larger to the mean square of the between groups, yielding an F ratio of approximately 1 or less. What all of this is saying is that when there's no treatment effect, the error or the variability within groups will be bigger than the variability, or equal to the variability between groups, and my ratio will be 1 or less. Okay, so what I want to say here is that when my F is bigger, it's easier for me to find statistically significant results. And the opposite. When the null hypothesis is false and the treatment effect is significant, the between groups variance is large, yielding an F ratio greater than 1. Here I put the larger the F ratio, the greater the difference between the group means relative to the variability within the groups. So the larger the F ratio, it's easier for me to find statistically significant results. This is the distribution of the F statistic, or this is called the F distribution. You have a different curve for different degrees of freedom, as you know, the same as T statistics, as chi-square statistics. Every distribution has a different curve for different degrees of freedom. And I put here, as every statistical ratio, it has a distribution. In this case, it's called the F distribution. Why? Because Fisher, okay? Because it was his name. So here, now we'll talk about a little bit about the critical values of T. Like T, the calculated F ratio is compared to a critical value to determine its significance. We know that because that's how all statistical tests works. Here, because mean squares are based on square values, the F ratio cannot be a negative number because we're working with square. Square values do not have negative numbers. And therefore, we do not distinguish tails in an F test. So because here you can see, if you don't have negative numbers because everything is squared, you start from 0. And if you don't have negative numbers, you won't be able to have a two-tailed test because things will only go from 0 to positive. Okay, here it says, a significant F ratio does not indicate that each group is different from all other groups. Actually, it only tells us that there is a significant difference between at least 2 of the means. So to see which group is different, we'll need to do a multiple group comparison. In this case, Bonferroni test. This is the F distribution table of critical values you have on every statistical book. This is a little summary. You'll see here the sum of squares, the degrees of freedom, the mean squares, the F statistic, which is the division of the between group mean square divided by the within groups mean square, and there you got your p-value. This is what you see in STATA. When you put the command one way, which is the command to do a one-way ANOVA, the command is one way, dependent variable, independent variable. Okay? So here you'll see sum of squares of between groups, sum of squares of within groups, degrees of freedom of within groups, mean squares of between groups and of within groups, your F statistics, and your p-value. Okay? Very easy. Now you understand everything of this, I suppose. Now, until now, we know one thing. Until now, we know that if we have an ANOVA with a statistically significant result, I know that I have one or more groups that are different, but I don't know which groups are different. So now I need to do my multiple comparison test, in this case, a Bonferroni correction, to know which groups are different. So for example, I'll go through this really quickly. If our independent variable have 4 levels, for example, why I do an ANOVA and don't just do many t-tests comparing all groups? Because if I do t-test, I will increase a lot my type 1 error. You want to see by how much will I increase my type 1 error if I do a lot of t-tests when I have 4 groups to compare all 4 groups? You see, to see how much my type 1 error increased, first I need to see how many comparisons I'll need to do to test all 4 groups against each other. And this little formula tells me that, which is my number of groups, 4 groups, okay? K is number of groups. So 4 minus 1, 3. 3 times 3, no, 4 minus 1, 3. So 4 times 3, 12. 12 divided by 2, 6. So I'll need to do six comparisons. So I'll need to do 60 tests. So now I can know how much my type 1 error will increase using this formula. This formula is for my family-wise alpha or family-wise type 1 error, which is 1 minus alpha, which is 0.05, time we exponentiate the number of comparisons, which will be 6. Okay. We see that. So you see here, if I have 6 comparisons, so if I have 4 groups, my alpha error will jump from 5% to 26.5%. So you don't want that to happen. Okay, you want to make your alpha stay at 5%. That's why we do a Bonferroni correction. So this guy Bonferroni was very intelligent, and what he did to maintain the alpha error in 0.5, when you have multiple comparisons, he just divided the alpha 0.5 by the number of comparisons, 6. So he gets 0.08. Okay, so this is your new alpha. So to be significant, your new alpha must be less than 0.008. This is all that Bonferroni did. Okay, I'll go quickly because I don't have much time. These are all the multiple comparison tests that we can use. Here you have Fisher, Duncan, Students, Dunnett, Stuckey, Sidak, Bonferroni is here, which is the most common, and Sheffis. Okay, you don't need to know any of this, just know Bonferroni. It works very well. This is our first STATA example. It's a one-way ANOVA example. Okay, I'll do it with you. Here we say we run an experiment varying the amount of fertilizer used in growing apple trees. We test 4 concentrations of fertilizer in 10 trees. Later in the year, we measure the average weight of the fruit. Okay, so let me go to STATA. Here's my STATA. Okay, so I have, this is treatment and weight are my variables for the apple trees, the weight of the apple trees, and treatment is the type of fertilizer. If I go to my data browser, I can see here that 2 trees had non-fertilizer, 2 trees had low fertilizer, 3 trees had medium dose of fertilizer, and 3 trees have a high dose of fertilizer. Okay, so we'll see how my one-way ANOVA goes. One-way ANOVA is really easy. Okay, you put the command for one-way ANOVA. One way, your dependent variable, which will be the weight of the apples, and your independent variable, which will be treatment. And you only pop that in, and you've got your one-way ANOVA table. You see here between groups, within groups, sum of squares, degrees of freedom, mean squares, your F statistic, which is 21, which is very high. Okay, so with a F statistic of 21, I know I'll probably be statistically significant. And when I do the hypothesis testing, look what my p-value is, 0.0013. So it's significant. Okay.
Sorry, I
so
can't see.
know what I know
sorry,
that.
Professor. We can see the STATA screen. Do you see the STATA screen? Because I just see the graphs from ANOVA.
You don't see my STATA screen here?
No, we don't. I don't.
I think it's a problem with your computer because I'm seeing it.
I see it too.
Do you see? Also go out and come back. Sorry.
Oh yeah, in the chat they are seeing the screen. I think
we can see.
Maybe I go out because I'm stuck in concept of ANOVA. I'm sorry. I go out and come back.
Can I ask a question?
Yeah, sure.
I'm sorry. I was wondering about the test of equal variance. Do I have to run separately, or when I do the command of one-way ANOVA, the STATA runs automatically? In
this case, STATA is really good at that, and they run the Bartlett's test for equal variance automatically. Here you can see on my screen. So here you have the p-value for the homogeneity of variance, which is 0.7, which means it's not statistically significant, which means that the variances are equal.
Okay, thank you.
Okay, here it is. That's right. So here in the one-way ANOVA, you can see that my p-value is 0.0013. So here you see that one group is different from the others, but which one? I don't know. So what should I do? A Bonferroni. I'll do my command once again. Weight, treatment, comma, put Bonferroni. It's really easy. And I have here this is my one-way table, one-way STATA table, and here's my Bonferroni. Here it says that my group with high amount of fertilizer compared to the medium amount is statistically significant. So there's a difference here. Also, the high with the low fertilizer, it's also significant. And here, the high with non-fertilizer, with the group of non-fertilizer, is also significant. So all these three groups are different, are statistically significant. Okay, while the medium with the low and the medium with the none, they are not significant, and the low with none is not significant. So here you see these three groups are statistically significant from the others. You know, and that's all you need to do. So I explained nearly like 40 minutes how to do an ANOVA, and you see in less than 10 seconds I got my one-way ANOVA done here with my Bonferroni. So this is the magic of software. Well, let's continue because we have a lot to cover.
I'm sorry, I have a question.
Yes.
Which one of the value in the one-way ANOVA table is the most important that I can say that there is a difference? The p-value or the statistic number?
The most important in your ANOVA is the p-value, because with your F statistic, if you will do it by hand with your test statistic, you will compare your test statistic to this big chart, big table with a critical value. If your F statistic is bigger than your critical value, then you will have a p-value less than 0.05. But here STATA gives you the exact p-value, which is 0.0013. So this is the most important part of your ANOVA table. Okay?
Thank you so much.
The p-value.
Thank you.
So here you know that with the p-value, you know that you got one or more groups different from the others. Okay, let's continue.
Wait, Walter, I have a question.
Okay.
Can you put the STATA again?
Sorry?
Can you put STATA again? I'll have a question with the bottom part.
STATA. Okay, okay. I'll put the STATA again here. Okay.
Thank you. Can you go with where was the ANOVA test?
ANOVA here?
Oh, well, here. That Barlett's test for equal variance. It says it's non-significant, but
yes,
what does that mean for my experiment?
When the Bartlett test for equal variances is not significant, it means that your variances, that your group variances are equal, that you have homogeneity of variance. Okay? If the Bartlett test is significant, then you have a problem because you have different variances. Okay? And then you will not be able to do a parametric test. You need to do a non-parametric test.
So in this case, I'm looking for a non-significant.
Yes, yes. In a Bartlett test, you are looking for a non-significant result.
That's great. Okay, thank you.
Okay.
Thank you very much.
Okay, excellent. Let's continue because we've got a lot to cover here. Okay, two-way and ANOVA. Two-way ANOVA, I won't show you any mathematics, any math, because if you understand the math of the one-way ANOVA, the math is nearly the same for two-way ANOVA, for repeated measures and everything. Okay, two-way ANOVA. It's used in factorial designs. Okay, it will be nice if you remember factorial designs. Factorial designs are used for efficiency. In factorial designs, you have two independent variables. For example, you can test diet and exercise and one output. Like for example, I want to see if diet makes my decreases my blood pressure. But I also want to know if exercise decreases my blood pressure. So instead of doing two trials separately, I'll do one trial which includes these two independent variables. So this is what I put here. Instead of doing two trials, you do one trial including both variables. It measures main effects and interactions, because as you have two independent variables, okay, you can have interactions between your independent variables. Okay, So that's one good thing about two-way ANOVA, that it can measure main effects and also interactions separately. But it's not a good idea to look for main effects and interactions in the same trial. Why? Because of sample size problems. I'll explain a little bit about this. For you to find main effect significance, you need a sample size much smaller than to find an interaction. So even if there's an interaction, if you are testing for main effects, your sample size calculations will be much smaller and you will not be able to look for interactions. Or your interactions will not be statistically significant in your trial, even though they really exist, because you have a low sample size, so it's underpowered for interactions. The other way around, if you're interested in looking for interactions, your sample size will need to be much bigger, okay? And so then you will find interactions. But what is the problem of having a bigger sample size? That if you have a much bigger sample size than what you need for main effects, then your main effects will always be statistically significant, even though maybe they are not clinically significant. So you should never test for main effects and interactions at the same time with the same sample size. That's one important point to put in factorial designs. The STATA command is very easy. You don't use the one-way command. You now use the ANOVA command, okay? This ANOVA command, here is, ANOVA command is your weight loss, which will be your dependent variable, diet, which will be your first independent variable, exercise, which will be your second independent variable. And if you want to test for interactions, you put diet / or this sign, which I don't know how it says, exercise, okay? Let's see how it works. For example, here there's a two-way factorial design, a 3x2, testing the effect of modality, for example, ice, splint, or rest, and medication, NSAID, and no medication, on change in pain-free elbow range of motion in patients with tendinitis. So I have patients with tendinitis, okay? And I want to test the range of motion of these patients. And I have one part of my factorial design is medication. I want to test my range of motion in patients which are using NSAIDs and patients which are using no medications. And the other part of my design will be testing range of motion in patients with tendinitis, in patients which receive ice, or they've got a splinted elbow, or their elbow is at rest. So that's more or less how factorial design works. So this is just to understand a little bit. For example, here you see the data, no, and NSAID, no med, ice, splint, rest. Here you've got the marginal means. The mean for patients with NSAID, the range of motion is 33.33. With no meds, 23.33. If you put ice, the range of motion is 40.50. Splint 29. Is rest is 17. So these are the marginal means. Okay. So you do your ANOVA, you do your command, and here you've got your sum of squares, your mean squares, your F statistic for modality, which is ice, splint, or rest, for medication, which is NSAID and no medication, and for the interaction, modality times medication, okay? We'll see the significance over here. Over here, okay? We see that for modality, there's one group or more that are different because it is significant. For medication, also, there is a statistical significant difference between the two groups, but the interaction is not significant. Okay, so that's how a two-way ANOVA works. And then with a two-way ANOVA, you need, if you want to know which groups are significant, you need to do a multiple comparison test of modality and another multiple comparison test of medication. So this is our second example, which is a two-way ANOVA example. Okay, here is I'll read it to you. We wanted to run 2 trials. One looking if different levels of salt in the diet increases the systolic blood pressure of participants. And the second trial consisted in evaluating if smokers also have an increase in systolic blood pressure. So salt, and the other part of my trial, and my other trial was smokers. So I want to do 2 trials. Sadly, COVID-19 destroyed our economy and we didn't get funding for the 2 trials, but only for 1. So after a lot of thinking, we decided to pursue both hypotheses using a factorial design. So I'll go to ANOVA and see how that works. I'll go to STATA, sorry. So here you have, in the database, you have salt diet, smoker, and my dependent variable, or my outcome, which is increase in systolic blood pressure. If I go to my data browser, you'll see here salt. I have 4 groups: patients with low salt diet, patients with normal salt diet, patients with high salt diet, and patients in a super high salt diet. Okay, and my smokers, they are or non-smoker, or social smoker, or smoker. 3 groups. So this is a 2-way ANOVA for a factorial design, but a 4 times 3 factorial design. Okay, and these are my changes in systolic blood pressure. Yeah, super high salt diet. That's funny. Okay, let's see how that works. Now I don't use the one-way command, but I use the ANOVA command, because the one-way is only for one way. ANOVA command is a more general command that you can use it also for one-way, for two-way, for repeated measures, for all the types of ANOVA, parametric ANOVA. Okay, we'll see. ANOVA, I put my outcome or my dependent variable first, which is systolic. Okay, then I put salt, which is my first independent variable, and now I put smoker, which is my second independent variable. And if I want, I can search also for an interaction, but salt and smoker. Okay, this is the command, and I will now run my STATA. Look how fast this is. I love it. Wow, you see? Here is my STATA output. What did my STATA output say? First of all, if I look at my adjusted R squared, it means that it is 0.32. What does my adjusted R squared means? You'll learn this in regression because you use the same R squared. It means that this model explains for 32% of my variability so meaning that there is 68% of the 68% of the variability that is not explained by this model. So maybe I could add some variables to increase the accuracy of my model. Yes, doing this by hand is like 2 days of work. You know, it's horrible. So let's see now what I want to do. Let's see my salt. What says about my salt diet? My salt diet, these are my sum of squares of salt diet, my degrees of freedom, my mean squares, my F statistic, and it's statistically significant. So we see here that one or more of the salt groups is statistically significant for increasing my systolic blood pressure. Okay, my smoker groups, we see that my F is 1.88 and it's not significant. It's 0.16. So this means that smoking does not increment my systolic blood pressure. Remember, this is only an example. This is not real data, okay? You all know that smoking increases your systolic blood pressure and it's bad for your health. So don't smoke. And the interaction, which is salty diet and smokers, it's also non-significant, 0.39. So from here, I can know that a salty diet, one of the groups of the salty diet are different from the others. Now, how I know which group? Can I do a Bonferroni in two-way ANOVA?
Can I ask a question?
Sadly, Ludwig, we cannot do a Bonferroni in a two-way ANOVA. But what we can do, remember, this is like salty diet is like one trial and smoker is like a second trial. Right, so what can I do right now? I can do a one-way ANOVA only of my salty diet, okay? Because it was significant. So I'll do a one-way ANOVA with a Bonferroni. Just look at this. One-way systolic salt. And we have my one-way ANOVA only of the salt part, okay? Which says that my probability is the same. It says that that one group is different from the others. I don't know why. What group? And now I'll do the Bonferroni, okay? One-way systolic salt, Bonferroni. But
can I ask you a question?
I can do the Bonferroni directly from a two-way ANOVA. I need to do a one-way ANOVA of the salt part of the trial, and then I do a Bonferroni, and let's see.
Can I ask you a question?
Yeah, sure.
Yeah, why you're gonna run another ANOVA if you already knew that was a difference between the variances? I mean, you have this information already.
Because the Bonferroni can't be done in a two-way ANOVA. The only reason I'm running this one-way ANOVA right now is to get the Bonferroni. Only for that.
See.
Only to know which group is different from others.
Thank you.
Can I ask a question as well?
Yeah, sure.
If the interaction of the two groups, the blood pressure and the smoker, were significant, what can I do?
If the interaction was significant,
yes,
then you need to test for interaction. You need to test for the interaction, for what part of the interaction is significant and what not. That's much complex than doing this, and then you need to do pairwise comparisons of all the interactions, of all the parts of the interaction. So it's like I can explain you that, but I'll take like 1 more hour. So it's very complex. Okay.
Thank you.
If you have my recommendation, if you have an interaction, which is a two-way ANOVA, if you have an interaction there, call a statistician to help you, because it's really difficult. Okay.
So we can only do like this test you're showing us, the two-way ANOVA, if there is no interaction. It'd be easier. But
yes,
it's possible
if
to
there's no
do.
interaction, is much easier. I think, and if you have no interaction, then and you have a significant result in your two-way ANOVA, then you can do a one-way ANOVA of that part.
Yes, I got that. Yes, thank you.
Okay. Okay. So here we see which group is different. So we see that the super high group salt has statistically significant differences with the normal group salt and with the low group salt. Also, the high group of salt, the high diet salt group has statistically significant difference with the normal and with the low. So there are 4 groups which are statistically significant in the salt diet. Okay, that's how you work with a two-way ANOVA. Now, let's go here to see repeated measures ANOVA. Okay, repeated measures ANOVA is used for pre and post test, like it's like a per T test, but this is done when you have more than 2 measurements per patient. Okay, if you only have a pre and a post, you'll do a per T test. If you have 3 or more measurements per patient, then you can do a repeated measures ANOVA. Okay, some difference between this type of ANOVA and the other type of ANOVA you have studied are that here there's only 1 group of subjects, not 3 or more groups like in other ANOVAs. The importance lies in the repeated measurements within each subject. So here the importance of the group is not that having 3 or more groups, but that each patient has repeated measurements. So these repeated measurements will act as different groups. Okay. So This is the opposite as all the other types of ANOVAs. Here, the within group variance, which was normally the error, now serves as the treatment effect. And the between group variance, which was the treatment effect in other types of ANOVA, here becomes the error or the error variance, okay? It swaps. And why it swaps? I told you, because here is not important the number of groups, because you have only one group. Here what is important is the number of measurements, okay? So within one patient, you will have your within group variance, which was before your error, will now be your treatment effect, because the patient will change scores every time they have the drug, or every time they do the outcome they have to do. Okay, this repeated measures ANOVA is not widely used because there are better models available to do repeated measures or longitudinal data. For example, generalized estimating equations are much better and much general than repeated measures ANOVA. They are much more helpful, but also they are much more complicated and much more difficult to understand or to use. But nowadays, when you have repeated measures, normally statisticians will use generalized estimating equations and not repeated measures ANOVA. But as we are in an ANOVA class, we'll study it right now. Here, this is a small example, okay? Sorry, I'll put play here. This is to illustrate the repeated measures approach. Consider a single factor experiment designed to look at differences in isometric elbow flexor strength. Okay, my outcome will be isometric elbow flexor strength with the forearm in 3 different positions. So I'll measure flexor strength in pronation, in neutral position, in supination. Okay, so this will be my repeated measures. 3 repeated measures. Okay, neutral, pronation, supination. So the independent variable forearm position has 3 levels. Here you see. No, I have how many subjects? 9 subjects. Okay, 9 subjects, which will repeat the elbow, which will repeat the elbow flexor strength in 3 different positions. So that's my repeated measures. So I have the mean of the flexor strength position. I see that the mean in supination has more strength than in neutral position and has more strength than in pronation. Okay, so I will do my repeated measures ANOVA. Before I do my repeated measures and my repeated measures ANOVA, I need to do one test, which is called the Monthly test for sphericity. Why? Because this is correlated data, because this is data within the same subject. Okay, so these are not independent samples, and this correlated data will alter my parameter estimations. So what this monthly test for sphericity does is they adjust my degrees of freedom depending on how correlated my data is. Okay? So if I find the monthly test of sphericity significant, which here it is not, then I will adjust my degrees of freedom by using the greenhouse geyser epsilon procedure or the Huitfeldt epsilon procedure, but only if my monthly test for sphericity is significant. Here, my monthly test is not significant, so I do not have to worry about altering my degrees of freedom. But remember, this is done because this is a correlated sample. Okay? So here I can see my test of within subject effects, which is position. Position will be my within subject and will be my repeated measures and will be now my treatment effect. In position, which can be pronation, neutral, or supination. We have 3 groups of position. This is my sum of squares, my degrees of freedom, my mean square, my F statistic, which is significant. Okay? And here is my between subject effect, which is the difference between participants, which is only my error variance here, which is not so important right now. Okay? So here I say, here I see in my combined summary table that position, which is my within within subject variability, which now becomes the treatment effect, is statistically significant. So here I say that one group is different, at least one group is different than the others. So how do I know which group? When using repeated measures, I can do a Bonferroni. So thank God I can do it. So we go to our example number 3. Example number 3 for repeated measures ANOVA, okay? So for this longitudinal study, we ask 5 participants to drink 4 different alcoholic beverages, 1 beverage each day. And we measure if there was an increase in the reaction time, okay? So it's drinking 1 alcoholic beverage to see if there is an increase in the reaction, it's a decrease in the reaction time. So they become slower, you know, and we'll see which type of beverage has the slowest reaction time. So we'll go to STATA and see how this works. Here I have person, alcohol, and my reaction score. I go to my data browser and I see here, I have 5 persons. 1, 2, 3, 4, 5. Each person take 1 day, person 1 took rum, the other day took vodka, the other day took beer, and the 4th day was tequila. And the second person, the same, rum, vodka, beer, tequila, and that's the way. Here you see that this table is different than the other tables, because here you have the same person repeated 4 times. This is a table called a long table. The others are called wide tables. Remember, to do repeated measures, you always need to put your table in a long position, not in a wide position, because if you put it in a wide position, STATA will not be able to run a repeated measures ANOVA or a repeated measures anything. Okay? So there are commands to change your table from wide to long. Okay, but here is long. Here is in the long format just to make things easier. Okay, so let's see. Okay, let's do our repeated measures. Okay, repeated measures. Okay, so we'll do the ANOVA. We'll put my dependent variable, which is score. I'll put my independent variable, which is person, and we put here repeat. I think it's alcohol. Let's see if it works. Nope. So let's do this again. I don't remember exactly how the command worked, but score person, here I think it's alcohol again. Okay, this is the command. Here you need to put ANOVA, your dependent variable, then you need to put your first independent variable, which is person, your second independent variable, which is alcohol, and then you put repeat, which is the variable which is repeated, and it's alcohol, and that's all your command. Okay, so here we see that my within within variance, within group variance, which is the one which show me treatment effects, is alcohol here, not person. Okay, here we see that my treatment effect is significant, meaning that there is one or more groups which are different from each other. But you remember the sphericity? Okay. So 0.0000 is my p-value. But here, STATA does the monthly test, okay? And the monthly test, they find the test significant. And so here they adjust automatically your p-value to one of these three: the geyser, the Hein-Fein, and the box. I always use the box because the box is much more conservative than the other two, okay? So the p-value, which was 0.000, was adapted because of the correlated variance, was adapted to was changed to 0.0076, which is also significant, okay? But this is your real p-value because we needed to adapt for the degrees of freedom because of the correlated data. But so, it's also significant.
Sorry, I have a question. What's the meaning of model here?
Sorry, I didn't understand.
Another table. You see the model, alcohol, person. Maybe you can move to another. The mode. See this another table. Do you mind?
Sorry, I don't get it because the audio of my computer is a bit it's not working good. But sorry, but if you can write the question in the chat, I will answer it for you like really quick. Thank you. Okay. So this is your actual p-value, okay? And we know that one or more groups are different, but which ones? We'll see. Let's try to do this with Bonferroni. Let's see if it works. Hopefully. Uh-oh. No. Well, I don't know how to do the Bonferroni in a repeated measures in STATA, but the other thing you can do is you can do like a pair t-tests also to see which group is different, or you can do Bonferroni, but I really don't know what how to do the command here. Okay, comma before Bonferroni. Let's see, because I put one comma here. Okay, let me see if with a comma before Bonferroni works. No. Okay, I'll search it and I'll send it you, and I'll send it by mail. Okay, let's go. Okay, let's go with Kruskal Wallis because we are a little bit late. Let's see with Bon. No. Okay, let's see. I'll search it and I'll send it via mail. Sorry. So, non-parametric ANOVA, Kruskal Wallis. No, the full name of the test is Kruskal Wallis one-way ANOVA by ranks. Kruskal Wallis is the parametric counterpart of a one-way ANOVA. So you use it when you don't comply with the assumptions for a one-way ANOVA, you go and do the non-parametric ANOVA, which is the Kruskal Wallis. Okay? As all non-parametric tests, it works by ranking the scores and working with the ranks instead than with the actual scores. The only assumption necessary are that samples are independent and that groups were randomized. Here you don't have the normality assumption or the homogeneity of variance assumption. Okay, the mechanism of the test is similar to a one-way ANOVA. The statistic used is an H statistic instead of an F statistic. This is the formula. You just need to fill in the gaps. Okay, here. Oops. Let's put play here. So here is first thing you need to do is to rank the data. So you rank it from low to high. So you have 110 is the rank is number 1. The second lowest rank is, I think, 25. But you see, how can you get 2.5 here? Because 25, you have how many 25? 1 and 2. So it would be 125 would be rank number 2, and the other 25 would be rank number 3. Okay? So you sum 2 plus 3 is 5. Divided by 2, because there are 225, is 2.5 each rank. Okay, that's how you rank scores, and that's how you rank ties. That's very easy. Then you rank this, and every group, you sum the ranks. You sum the ranks of every group, okay? Then you fill in the gaps, okay? When you use the H statistic, N will be the total sample size. In this case, 14, okay? Here you put 14 because this is the total sample size. 14, then small n is the sample size within each group, okay? Here, the sample size within each group is 5 in one group, 5 in second group, and 4 in the third group. And R is the sum of the ranks within each group. You remember, the sum of the ranks are 27, 29, and 49, okay? Oops, sorry. So here you just fill in the gaps, here, here, and here. Then you put here total sample size, which is 14, and then you do the math, and then you've got your H statistic. Your H statistic is tested with the chi-square distribution, with k minus 1 degrees of freedom. In this case, we have 3 groups, so it will be 2 degrees of freedom because k is number of groups. Okay. Then the calculated value must be equal to or greater than the critical value to be statistically significant and reject the null hypothesis. So that's as every statistical test. Okay. So we see here my H statistic was 7.34. Then I've got my p-value is 0.025, which is significant. Okay. If you find a significant result, then you need to do a multiple comparison test, as in every ANOVA type of test. Here, for Kruskal Wallis, you don't use Bonferroni, but you do the Dunn's multiple comparison test. It can be used because the Dunn works for non-parametric ANOVAs. Okay. That was the Kruskal Wallis, which was the counterpart for the one-way ANOVA. Now, this is the Friedman test, or the Friedman ANOVA. The Friedman is the non-parametric counterpart of the repeated measures ANOVA. So here, no assumptions are needed for this test, okay? The ranking process is similar to other non-parametric tests, but they are done on the repeated measures within each subject. As you know, you need to rank the scores. Here, not the chi-square, but not the H statistic, but the chi-square R statistic is used. Sorry, this is the formula for the chi-square R statistic. You also need just to fill in the blanks. So, as I told you, how you rank the data in Friedman, which is repeated measures, okay? Remember, the other one, you rank from the lowest to the highest. Now, your ranking is across subjects, so horizontally, okay? You rank it all across subjects. So, 110, 150, and 175 is 1, 2, 3. Here, 120, 130, 135, 140, the same, 1, 2, 3. And where there are ties, it's like this 100 is 1, 100 is 2, 1 plus 2, 3 divided by 2, 1.5, 1.5, and the other 110 will be 3. You rank horizontally here, but when you sum the ranks, you sum them vertically, okay? And this is what you will put in your chi-square R statistic. You'll see it here. You fill in the blanks. When you use the chi-square statistic, small n is the number of subjects. Small n will be the number of subjects, 6 subjects. K is the number of measurements, which will be 3 measurements. And R is the sum of the ranks for each measurement. Here you put the sum of the ranks. You fill in the blanks, then you have your chi-square R statistic, which is 9.25, okay? Then this is not H, it's chi-square R. Then this chi-square R statistic is tested with the chi-square distribution with k minus 1 degrees of freedom. The calculated here will be 3 groups, so it will be 2 degrees of freedom. The calculated value must be equal to or greater than the critical value to be statistically significant and reject the null hypothesis. That was non-parametric ANOVA. Okay, sorry that I'm running a little bit, but this is the same. But I need to do correlation. It's only 10 slides. I'm up with my time, so everyone, I'm so sorry. You all are. If you want, you can go. If you want, you can stay. But I will continue with the lecture is only 10 more slides. Correlation is 10 minutes. Okay, and yeah, let's go. Correlation. So this is completely different from analysis of variance. Okay, the basic purpose of correlation is to describe the association between two variables. Okay, remember, correlation is association between two variables. It's used for continuous data. Here, both variables must be continuous, both of them. Okay, so the association between variables is based on the study of covariance and can be positive or negative. You can have a positive correlation or a negative correlation. Okay, so the best visual way to analyze these relationships or association are with the use of scatter plots. And also, correlation coefficients will describe the strength and the association between variables. Okay, we'll see here. These are my scatter plots. So here we have one continuous variable on the x-axis and one other continuous variable in the y-axis. No? These two variables depend one on each other. This is a perfect positive correlation. It's perfect because all the points are in a straight line. Okay? This is my correlation coefficient. When it's perfect, my correlation coefficient is 1. Here I've got a perfect negative correlation, meaning that first I'll go with this one. This means that when variable in the x-axis increases, the second variable also increases. This is called a positive correlation. This is called a negative correlation because when one variable increases, the other one decreases, okay? And it's a perfect negative correlation because because you see that all the points are in a straight line and my R here is -1. So correlations can be from R1 to R-1. R0 means there's no correlation between variables. Okay? R equal 1 is a perfect positive correlation between variables, and R equal -1 is a perfect negative correlation between variables. And yes, here I have a question. How do we test for linearity? Yes, only with a scatter plot. For correlations, you only test for linearity with scatter plot. For regressions, there are much complex way to test for linearity. The other question, when we perform Pearson correlation, I'll show you in a bit about Pearson correlation, don't worry. And can I use a correlation to test a hypothesis or just for secondary analysis? Correlations are just to see, you can test hypotheses with correlations. Yes, I have that in the next slides. You will see that. Okay, this is also a positive correlation, but it's not perfect. CDR is 0.98. This is also a positive correlation, but it's much less perfect with an R of 0.78. This is a negative correlation with an R of -0.70. You see, it's not that exact. And this correlation is very poor, or there's no correlation here because you have an R really, really small, really close to 0. Okay? Now, correlation coefficient. What I show you here, this R is called the correlation coefficient, okay? It's represented by a lowercase r. It quantitatively describes the strength and direction of a relationship between two continuous variables. In other words, it quantitatively describes the strength and direction of a correlation, okay? The coefficient can take values from -1 to 1, where a value of 0 means there's no relationship between the variables. So here, I told you the correlation coefficient describes the strength and direction. The sign of the coefficient describes the direction. Positive sign is a positive correlation. Negative sign is a negative correlation, okay? While the actual number relates to the strength of the correlation. A correlation close to 1 is a strong correlation, is a strong positive correlation. A correlation close to -1 is a strong negative correlation. So this is a rule of thumb of the correlation coefficients. If my correlation coefficient is less than 0.25, there's a poor or no correlation. If my correlation coefficient is from 0.25 to 0.5, it's a low to fair correlation. If my correlation coefficient is from 0.5 to 0.75, it's a moderate to good correlation. And if my correlation coefficient is bigger than 0.75, I have a strong correlation. This is only a rule of thumb, but it works, okay? These values should not be used as strict cutoff points. Their interpretation is affected by sample size, measurement error, and types of variables studied. For example, sample size, okay? If I have a super big sample size, a sample size of like 3,000 scores, and I do a correlation, if I have a correlation coefficient of 0.10, which would be a poor or no correlation, that correlation coefficient will be statistically significant just because of the big sample size. Okay, so so you need to be very careful with this rule of thumb regarding sample size. Okay, and please remember, this is the most important thing I will talk to you about correlations. Remember this: correlation does not mean causation. Why do I tell you this? Because of this. See, this is a nearly perfect correlation. Forget the line, because their correlations do not have lines. If you put a line here, it's a regression, okay? Correlation are only the dots, but I put this because I like this. This scatter plot has a correlation of 0.99, and it says that the margarine consumption per capita is nearly perfectly correlated to divorce rate in Maine. So this means that when you eat more butter, you have much more chance of divorce. Okay? So you see, you can find correlations everywhere. Correlations are only associations, okay? They don't have any causal relationship, because to have causal relationship, you need to have a randomized clinical trial, and correlations are used normally in exploratory designs. Okay? So correlation does not mean causation. Please, please, please remember that. Too much margarine, I know. Okay, I'll continue. What are the assumptions for correlation? Data must be continuous, that each subject contributes to a score of X and Y. So there must be a covariance between both scores. The data must be normally distributed when looking for Pearson correlation, okay? Only for Pearson. If that is not normal, you can use Spearman's correlation, so don't worry. And this is important. X and Y are independent measures, so that one score is not a component of the other. So it's not fair. It's not fair, and it's not the right way to do correlations, to use dependent measurements. They must be independent. Okay? For example, gate velocity and distance travel. Why this is not a good correlation? Because it's because this will have always a really good correlation. Why? Because velocity has distance within it. Because velocity is distance divided by time. Okay? So these two variables are dependent. Okay, so you can't do a correlation between these two variables because they are dependent. They are not independent. The two variables should be independent, so the correlation means something. Okay. Now, what's Pearson? Pearson product moment correlation coefficient is the full name. This is only the R I told you before. The correlation coefficient, or R, is the Pearson correlation coefficient, because we are working with parametric data. This was developed by English statistician Carl Pearson. Okay, it's the famous R statistic correlation coefficient we've seen in the last slides. It's used for parametric data. This is the formula. I'll not go into it because we don't have time. the product moment correlation coefficient can be subjected to a test of significance to determine if the observed value is significantly different from 0, okay? The null hypothesis states always that there is no relationship between these two variables, making the correlation coefficient equal to 0 in the population. The alternative hypothesis states that there will be a relationship and the coefficient will not equal 0. Here, your null hypothesis is that your Pearson correlation coefficient will equal to 0. And your alternate hypothesis means that your Pearson correlation coefficient will not be equal to 0. Okay? R has its distribution with critical values for the different degrees of freedom, which in this case is n-2. Always that you use a Pearson correlation coefficient, your degrees of freedom will be n-2. The observed value of R must be greater than or equal to the table value to be significant. So put it in another way, the observed value of R must be greater than or equal to the critical value to be significant. Okay? What does a significant correlation means? What does a correlation which have a p-value of 0.05 means? It has nothing to do with the strength of the correlation. It only says that the correlation is not likely done by chance. Okay? So in correlations, I find it much more important the strength of the correlation than if the correlation is significant or not. But yes, you can do hypothesis testing with correlations, with Pearson when it's parametric and with Spearman when it's non-parametric. How? Like this, as I told you here. So for example, there is a scatter plot of ambulation and cognitive status in children with traumatic brain injury, okay? So as the cognitive status increases, the ambulation score increases. So this is a positive correlation. It is a correlation of 0.348, so it's a 34% correlation. It's not a good correlation. You can see it's more like a cloud, but it's significant with 0.001. So it's a poor correlation with a significant value. That's all. Now, the other type of correlation we need to know is the Spearman rank correlation coefficient. This is the counterpart of the Pearson, but it's used for non-parametric data. Okay? This ranks the scores as most non-parametric hypothesis tests. It uses the RS or Spearman's raw statistic. It's not the R, it's the RS. Okay? RS as well has its distribution with critical values for different sample sizes. Here in Spearman correlation, we do not use degrees of freedom. We use the actual n. We don't use n-2, n-1. We use the actual n in Spearman. Okay? Then the observed value of RS must be greater than or equal to the critical value in the table to be significant. So here is a Spearman rank correlation coefficient example. Here, ranks correlation using Spearman and Kendall et al. Verbal and reading comprehension scores. Here says that if you have a verbal comprehension, a higher verbal comprehension score, your reading comprehension score will be greater. So this is a positive correlation also. You see it's a 0.8 correlation. The correlation coefficient is 0.8, so it's a strong correlation, and it's also significant. Okay? Now, this is my last slide. We'll do a STATA example of correlations, okay? Here we see, we have different 1978 lowrider cars, and we want to see if the weight of the car is associated with gas consumption, okay? So we'll go to STATA. There's my STATA, that is here. So we'll use the last two variables, which is pounds and miles per gallon. Okay, we go to our data browser and we see here pounds, how much weight each car, and what are the miles per gallon of each car. Okay, so now we'll do our correlation. Okay, the correlation command for Pearson is PCOR. Let's ask PCOR, LBS, MPG. Okay, here we do our correlation. Huh? What happened here? Too few variables specified? Weird. Let's see again. Core, LBS, MPG. Okay. Here is our correlation. You can see. It's the correlation for pounds and miles per gallon is minus 0.8. Okay, so this means that it's a negative strong correlation, meaning that the more the car weighs, the less mile per gallons it has. Okay, so the more gas you should put, the more it consumes gas. Okay, so this is a negative strong correlation. So it's an inverse correlation. Okay, and correlation is very easy. So you can see correlation is one special type of statistical test, because it is a symmetric test or a supersymmetric test, meaning that it doesn't matter the order I put my variables. If I put MPG and LBS, as I put first LBS, MPG, if I put MPG and LBS, it will give me the same result. It doesn't.
Can I ask you a question?
Yes, sure.
Yeah, can you do a scatter plot using STATA?
Yes.
Or this is...
I'll do scatter plot right now. Sorry.
Okay, thank you.
I forgot. Scatter, LBS, MPG. Here you have it. You see? This is a...
Yeah, thank you. It's better to see now.
Correlation. Yes, car weight, gas consumption. So the more my car weighs, the less mile per gallon it will give me. So it's negative correlation. Okay, it's very easy to do. Correlations in STATA are very easy to do with the core. I just want to do one more thing. Sorry. PW core. I need to see just one small thing here. Correlate. P core. I just want to do SIC. Okay. Now, if you want to PW core, LBS, MPG, SIC. Okay. When I only want to see my correlation coefficient, my Pearson correlation coefficient, I do the core. I use the core command. Okay. If I want to see my correlation coefficient and if it is significant, I use the PW core command and put LBS MPG, comma, and put SIC of significant. Okay. And I will have here my correlation coefficient, and it says it's really significant. Okay, it's really easy. So that was all I had to talk about correlations. Correlation is much easier than ANOVA, as you can see. And my last slide is, oh no, which I don't have my last slide. This is my last slide. Thank you guys. So if you have any question, I'll be happy to answer for you, but I think we are on time. If you want, you can send me any doubts or any answer via email. I'll be happy to answer you. Sorry, I'll put my email here if you want.
Thank you, Walter. It was a great lecture.
That's my personal email. So yeah. Thank you very much, guys. And I'm so sorry I've passed my time, but it was important for you to understand all the ANOVA and correlation things I had to tell you.
Great lecture, Walter. Compliments. Great lecture, Walter. Compliments.
Thank you.
Thank you.
Thank you.
Walter. And then Everyone, thank you for your participation. And if you have any question, please email to me, Walter, anyone, any TAs, and we can try to answer. We try to answer, okay? And sorry, maybe I cannot respond to everyone's question. If you have remaining doubt, please contact us, okay?
Okay, here you are. Okay.
Thank you.
Thank you, bye-bye.